belongs to the code, then the shift of the element is also in the code. This is a very old definition by Branch, and essentially it was introduced because of hardware. It was used in those times the computers were slow, and they would work better if the code was cyclic. But it has an interesting consequence. Let's go. If we consider this ring, this factor ring, it's easy to see that we can map a code from Fn here in the most natural way. An element goes to the polynomial that has these elements as coefficients. And it's very easy to see that linear code is cyclic if its image here is an ideal. So this was done for material reasons, say, but it has an advantage. We can work with codes using whatever we know about polynomials, Galois theory of finite fields, and things like that. On the other hand, if we take a cyclic group and we consider the set of all linear combinations of these elements, it's very easy to see that that set, which we denote like this, is isomorphic to this factor ring. So to study cyclic codes is equivalent to study ideals of a group algebra of this form. Now, if they are, oh, sorry. If they are, no, this is the point. Okay, if they are isomorphic, what is the advantage to change from one to another? Well, it's more or less like what happens when we work with representation theory. If we're working with a group, we use properties of the group. If we represent it as a group of matrices, we can use elements from matrix theory, like determinants, traces, and so on. Here is the same situation. For studying a cyclic code here, we will use essentially, say, Galois theory over finite fields. But if we work it here, what we will use is properties of the group. So we shall use group theory to study cyclic codes. And this has been generalized. A group code is an extension of a cyclic code. It's simply an ideal of a finite group algebra. This definition was introduced by Berman and McWilliams in the early 70s or so. And if we wish to study ideals of a finite group algebra, in what follows, I will always assume that the characteristic of the field does not divide the order of the group. So the group algebra is simple, meaning that every ideal of the group algebra is generated by an idempotent. So essentially, to study group codes under this assumption is equivalent to determining or studying idempotents in the group algebra. When you work with group algebras, as was my case before I even heard about Códigos, when you work with the structure of group algebras, there is a very natural way to introduce idempotents. If H is a subgroup of a finite group G, and we are in the same simple case, then we can construct this element. We simply consider a linear combination of elements of the group, which is formed by adding all the elements of the subgroup and dividing by this coefficient. This is it's very easy to prove that this is an idempotent, and it's called the idempotent determined by H. And it's very easy to prove that this idempotent is a central idempotent if and only if H is a normal subgroup of G. Actually, there are a lot of things that are known in this situation. The ideal generated by this idempotent is isomorphic to the group algebra of the factor group. And when we use codes, it's very useful to know a basis of the code. And in this case, it's easy to find a basis. Let tau be a transversal of H in G. By this we mean a set of representatives of cosets. And then it's easy to show that if you take H hat, this is the idempotent, multiplied by T bar I in the transversal, this is a basis of the ideal. So, what are the essential idempotents? This, when we work, we try to produce some coding theory with groups. In the group algebra, it's more or less natural to try to study first the minimal ideals, because it's very well known that any other ideal is a direct sum of minimal ideals. So this has been done by a lot of authors, including myself, and in a certain ways was not so smart, because when you're doing algebra, you want to know the structure of ideals, then it's natural to do that. Try the minimal, all others that come from those. But if you're thinking about codes, then it's not so natural, because the minimal distance is not an algebraic property, it's combinatorial. So it doesn't work so well. But anyway, there are a lot of things in which minimal ideas are important. We shall see some, and in the next few talks you will hear more about this. When you have a group algebra, the group algebra is a direct sum of its minimal two-sided ideals. These are generated by some idempotents in ES. These ones are called the primitive idempotents. And it's very easy to show that any two-sided ideal is a sum of these. It follows that every central idempotent is a sum of these. Those are called the constituents of that. So, assume that we have this H hat, and we take a primitive idempotent. So H hat is a sum of some of those. This primitive. And this form a set of orthogonal idempotents. So if I take one of the primitive idempotents and multiply it by H hat, I have to multiply all these by H hat. And what will happen? If E is none of these, then it's orthogonal to all of them, gives 0. If it's one of these, it gives E squared, it's being idempotent, it's 0. So there are only two possible results. And when this happens, clearly the ideal generated by the primitive idempotent is included in here. Now, any element of this ideal, is a linear combination of the bases. And this means when we write this explicitly, it looks like this. So you see a coefficient is repeated here, then this coefficient is repeated here, and so on, meaning that these ideals actually give rise to repetition codes. And repetition codes are not interesting. So, we don't want to have this possibility. So we say that a primitive idempotent is essential if this product is zero for every subgroup. So these are the primitive idempotents that do not give repetition codes. Ideals generated by these are called essential ideals. And it's practically trivial to show that the map that goes from G to GE, notice each of these components can be written as FG1, FG, yes. This is the same thing as this. So this map is just a projection into the components. This is a trivial remark, but it's very important. If you're working with an abelian group, for E to be essential, this has to be an isomorphism. But this is a group inside a simple component. If everything is abelian, the component is a field. So the group is cyclic. So this means that for an abelian group, essential idempotents exist only in the cyclic case. Well, this is not so interesting. This is a way to construct an idempotent which is the sum of all the essentials. This is the important thing. There is this E0, which is the sum of all the essentials, and you can show that in the cyclic case, this E0 is never zero. So actually, what you obtain, the important thing here, is this for all. And for an abelian group, essential idempotents exist if and only if G is cyclic. Why is this important? Well, quite some time ago, I was in a meeting on coding theory, and it was said that, somebody mentioned there, that since the times of Berman, when he introduced outgroup codes, there was not a single case known in which abelian codes would be giving something better than cyclic codes, which is very surprising because it's a much larger family. And the reason was perhaps because people were really working with minimal codes. And we were able to prove that if you take a minimal ideal in finite group algebras of abelian groups, they are combinatorially equivalent to minimal ideals in cyclic group algebras. That's the reason why we didn't find better codes. Then a student of mine working for the PhD, we compared codes on group algebras of a cyclic group of order p squared with ideals of a cyclic group of order like this, an abelian group, non-cyclic. Of course, for minimal ideals, nothing happened, but if we were able to prove that here are better codes than here. So But this was a long time ago. Later, we found this result that explains why we couldn't find things like that for minimal. And, well, let me go to as soon as you take a linear code, you say it contains non-zero columns. No non-zero columns if the generating matrix doesn't have a zero column, which is the same thing as saying that in the code there's not a position in which every coordinate is zero. That would be, you would be able to reduce it. So for codes like this, we were able to prove, this is one of the many applications of extension codes, that a code is of constant weight. Let's see here a linear code of constant weight. Now, binary, this is essential. And so the alphabet here is 1, 0, and 1. Then we were able to prove that a code of constant weight is equivalent to a cyclic code which is essential or a repetition of essential one. So the essentials play an important role here. And in those days, we tried quite hard to extend this to other finite fields, and we couldn't. And the reason was precisely because we were working with group algebras. There's a need to generalize the idea. We have to work with so-called twisted group algebra. What's a twisted group algebra? A twisted group algebra, the elements essentially look in the same way as if it were a group algebra, except that because it's not a group algebra, we denote these elements with a bar on top. The addition is defined as usual, and multiplication is given like this. The multiplication of two elements has a coefficient here. And elements and coefficients commute. And this mapping says that to each pair of elements of the group associates an element of the field has to obey this rule, and then it's called a twisting or a factor string or a cycle, several names. But that's the important thing. The important thing is that to multiply elements of the group, you have to add some kind of coefficient. Well, many results have been used via cohomology, but they can be obtained working algebraically with the coefficients. An example of a twisting, very easy, is the following. Assume that you have a cyclic group and take an element, a fixed element in the rate R. So to each pair Gi, Gj, you associate either 1 or lambda, depending on how the exponents behave. This is a twisting. But the interesting thing is that you can prove that every twisting somehow is equivalent to a twisting like that I mentioned before. And there is a proof using cohomology, but we produced a manual proof that has the advantage in this proof that the sets that you have are exactly the same with the same operations. The only thing you have to do is choose the basis differently. But the fact that this is the same thing, the same set with the same operations, allows you to work always with a twisted group algebra that looks like this. And then we'll prove these, and there are some results that I will pass by. This is not so important. And remember In the group algebra case, the group algebra was isomorphic to a factor ring like this with a 1 here. So that can be extended very easily with this result. Now, in the case of group algebras, we had this H hat that was an idempotent element. How do you prove that this is an idempotent element? You multiply it by itself. This looks like this. I just wrote the definition in one case. Then this looks like this. And if you multiply all the elements of a subgroup but by one of them, you obtain the same. Sorry, I forgot here. So you get this. And you get the H hat. So this is the very elemental proof that H hat is idempotent. But notice, this depends on the obvious fact that you multiply one element here by one element here by just doing the problem. When you have a twisted group algebra, if you want to do that, that introduces coefficients. So that does work. So it was necessary to find an equivalent of this H hat. So we do the following. Take a cyclic group. Lambda is the element of the field that gives the twisting. Take a root of this polynomial, so you have to go to a bigger field and construct this element. See, it looks like the other one, except that we introduce coefficients. But by doing that, we obtain really an idempotent, which is more or less, say, the extension of the previous concept. And the interesting thing is that if you take two different roots, they produce orthogonal idempotent. This was kind of a surprise, because in the group algebra case, one subgroup gives one idempotent. Here, one subgroup gives a lot of idempotents, depending on the roots. And the set of all the idempotents coming from the group gives the full set of primitive idempotents. Using that, it was possible, I will talk about that here, but using this idea, it's possible to fully determine the structure of the group algebra. Yes. Now, how to extend the idea of essential idempotent? This idea is due to 12 figures. So, given a subgroup, assume that you can associate to every element of the subgroup a coefficient in such a way that this happens. This is the twist. If that is so, you construct this element, and this element is a central idempotent of the twisted group algebra. And we say that the pair H and beta, beta being that mapping, is an admissible pair if this happens. And we can define a projective essential idempotent. Actually, the word projective is not very good, because he used projective because the origin of all this was projective representation theory. But the problem is that there's another concept of projective for ideas and modules which is not the same. So we actually we're trying to change the name to twisted essential idempotent. It should be noted the following. This is an extension, say, of the concept of essential and important, but not a very natural in the following sense. When the twisting is the identity, the twisted group algebra is the group algebra. But these twisted essential idempotent are not the essential idempotent. As I mentioned before, for the group algebra, the cyclic group, there always exists essential idempotent. And in the twisted case, it depends. If this polynomial splits in f of x, then there are no projective essential idempotent. So it's not exactly the same thing. It's the same idea, but it's a little bit more complicated. And it has a lot of consequences, which I will not talk about, but the next two speakers will show you that these essential idempotent are also involved. That's all. Thank you.
Questions, comments?
Maybe I have a comment or a question. So in the standard case from Códigos theory, right? Not the classical, let's say, McWilliams and Sloan. So the study of you consider the factor over x to the n minus 1. And then the factors of x to the n minus 1 define codes. And combination of those factors will giving you different distance growing or decreasing, but length going the other way.
Yes.
So now you have sort of similar case here with xn minus lambda that allow you to have this twisted situation. It has been studied also in this case, what happened with those factors. Do those factors give you codes, and how do they behave in terms of minimum distance and so on? Is the same situation of?
I think it's more or less similar, but I don't think it's been studied. At least we don't know. We've always looked at from the group theory point of view. So I don't know if it's in that.
I wonder whether it will be a similar sort of structure, for
I'm sure that there is.
Yeah,
it should be done.
Yeah. Exactly. I was thinking of that. This is like a constant cyclic.
Constacyclic codes, yes, exactly.
Actually, in the cyclic case, we have a general theory, so it's any group, not only cyclic group. The cyclic group we have constacyclic code, have a lot of
That's right. Here you have the difference, because you know what happened in the cyclic group, you already sort of
From the point of view of group theory, we have the description in the abelian case also, not only the set. The factors and.
But it's very nice to have it on the F. Very nice.
Any other comment, questions? So let's thanks again.
Eu não conhecia nenhum.
So let's go for our second talk. So it's going to be from Samir Assuena from Centro Universitário da FEI, in São Bernardo do Campo. And he is going to talk about the good LCD codes from twisted group array.
Thank you. Thank you all organized for giving me the opportunity to speak here. Special occasions, celebrating, nice my birthday.
Panalo si Sen.
I didn't want to say anything, but it happens to me once that I was giving a talk and someone said you have a typo the very first.
Yeah.
To you, you know.
In my case, it's always okay. You know, always have a typo in my
Exato, para essas galaxias maravilhosas.
But it's funny
maybe my student did this. So this is a joy to work with ANDRÉ from Universidade Federal Rural do Rio de Janeiro. And we are working on twisting group rings, using twisting group rings to study some kind of codes. Okay? These kind of codes are called constacyclic codes, and it's just in a natural way, generalization of cyclic codes. So we just take some units in the ring R. Here, the ring are finite commutative with identity. And what we have here, we have a linear R submodule of R to the n. It's called a linear code. And if we consider any code word, we just apply the shift and multiply the first coordinate by this element lambda here. Lambda here is a fixed element. We choose one unit here inside the ring. And if this, after this operation, the new code word belongs to the code for every code word, we say this code is cyclic code or lambda cyclic code. Okay. And the Hamming weight of any code word here is defined the number of coordinates that are different from 0, and the Hamming weight of the code is just the minimum weight of all code words in the code. Okay, as CÉSAR told us in a brilliant way, if we consider lambda equals 1, we have cyclic codes. Okay, and this kind of codes can be realized as ideals in the factor ring in this way. Okay, these for cyclic codes, but constacyclic codes can be also realized as ideals inside this factor ring. Okay, you just replace 1 by lambda, and you have basically the same result. And so, can we describe or realize this kind of codes in a different way? Yeah, the answer is positive, but we need to consider twisted group. Okay, twisted group problem. As CÉSAR told us, it's just a associative ring with bases different set, which we denote by G bar. The product here is defined as CÉSAR told us, G bar times H bar. We have just a coefficient here, and this coefficient has to be a unit in the ring R. Okay, and in order to obtain an associative ring, we have to not put this condition, but we can prove this mapping gamma must satisfy this equality, and for this reason, we prove that this mapping is a 2 cosine. Okay, if we do not put the associative condition, we don't have a 2 cosine. Okay, but in our case, all rings are associative, and we have this implication here. Okay. What happens in this case if we change this coefficient, this mapping, it's called a twist. If we change the twisting, we have different rings. Okay. In some sense, they are sometimes related, but we obtain different rings. In the case with this mapping is constant equals 1, we obtain exactly the group order. Okay? And here appear this twisting, which CÉSAR showed us. And this mapping is just exactly the same mapping that prove constant cyclic codes, or in the case of cyclic codes, constant cyclic codes can be also realized as ideals in twisted group rings. Okay? So exactly the same mapping, just if we do not consider the bars, we have the same mapping in the case of group order. Okay? So we can also see constant cyclic codes inside of twisted, as ideals in twisted group. Okay. So, in the case of cyclic groups, what happens is when you compute, for example, g bar square, of course, my definition is g bar times g bar, but we have here some coefficient that multiplies g bar, so g square bar. Okay? And so on, making these operations, computing the powers of the elements g bar. What happens is, in this case, we can replace these elements by g bar to the k. Okay? But the crucial difference here, when you compute g bar to the n, we have here lambda times 1, not exactly 1. When we obtain exactly 1, we are in the case of group algebras. Okay? So these are cyclic groups and commutative rings. Using this twisting, we obtain a commutative ring. Okay? We should be very careful here. Even considering, for example, abelian groups, commutative rings, when we look at this structure, we may obtain a non-commutative ring, even considering commutative rings and abelian groups. But in case of cyclic groups, we have always a commutative ring. Okay? So, how to produce or how to obtain good codes using this extraction? For this, to do that, first we consider sigma and automorphism of the ring R. The ring here is finite. Of course, the automorphism has an order n. So we define the generalized Galois form in this way. Okay, generalized. We just apply the power, the k power of the automorphism in the coefficients of element beta, and multiply coefficient by coefficient and take the sum of these elements. Okay, this is called k generalized Galois form. And we can, it's easy to see, when the k equals 0, we have the Euclidean linear product. But in this case, in the general case, we can define the k generalized Galois dual of the code. See, it's just the set of elements which are orthogonal to every element of the code. Okay? So what can we say about this set? In general, maybe it can be difficult, it will be difficult, but in the case of cyclic groups, or cyclic or constacyclic codes, we can give this description of this kind of sets. If we take a lambda constacyclic codes, it's generalized dual. It's also a constacyclic code, but we need to change the scalar here, the units in the regard. Okay, it's also a constacyclic code, but we need to take this element as a unit of the ring. Okay. So we say that code or twisted group code or twisted or constacyclic codes, in this case, it's a linear complementary Galois dual if the code intersects its K dual trivially. Okay, this is kind of K Galois LCD codes. Okay, and here we have some interesting results that shows us if these elements are different, then any constacyclic codes is LCD code. Okay. The reason here, to be more precise, when we take this difference, the only LCD codes is just the trivial ones. Zero space and the whole space, the whole. Okay, so these codes are, it's always LCD. So when this condition happens, we do not have some kind of space to work. Okay, so we have to assume this condition here to obtain non-trivial LCD codes. Okay, and how to describe this kind of codes? So when we look at the elements of the basis of the ring, it's not written here, but these elements are units in the twisted group ring. Okay, so we can consider the mapping that send any element into the we just are keeping the coefficient by taking the inverse of the elements dr. In the case of group algebras, this mapping is always an involution. But here, if this condition holds, this mapping is also an involution. Okay? If we take a look in the previous what it's here, in the case of Euclidean inner product, it's just a condition what we need. Okay? Just in case the Euclidean inner product K has to be 0, so this condition is equivalent to this. But if we consider the equality here, we have also have all the equality that we need. Okay. So this is the definition of the Euclidean inner product. Just when K equals 0. In this case, we can obtain this result. We can give this a precise description of this kind of LCD codes. LCD codes are those ones that have to be generated by an idempotent element, and this idempotent has to be fixed by this evolution. Okay. Here we have some words, some new words here. We are just considered finite commutative chain rings. What is a chain ring? There is a lot of characterization, but in our case, a finite commutative ring is a chain ring if it's Jacobson radical. It's a principal one. Okay. Why we are considering this? When we are studying LCD codes over chain rings, these codes are always free. In the sense, always all LCD codes over finite commutative chain rings has a base over. Okay, this result is more a little bit general. It can be proved also when we consider Frobenius rings. Okay, but chain rings are a particular case of Frobenius rings, and this condition is crucial for us. Okay. Okay, let me show you some examples of good codes. Okay, and just to recall, remember something like that. When we are considering fields, there are only two possibilities for lambda here. Okay, just one in the case of algebra, and minus one, and we have the so-called negacyclic codes. Okay, in the case of fields, we have just two possibilities here. Okay, so we are taking here the field, finite field with 3 elements, the cyclic group with 10 elements. It's not difficult to see here. I will just show expression of the idempotents here. This is just an idempotent. This group algebra. Maybe it's not a minimal one, but we are not interested in this. In the minimal ones, we are just looking for or searching for idempotents which are fixed by the inclusion. Okay, and this happens for this element, and the code generated by this element here has these parameters, and this code achieves the best, the maximum minimum weight known for this length and this rank in this case. Okay, and we produce some others kind of codes. Here, finite fields with 5 elements, the cyclic group with 21 elements. The group is greater than the best one, so we have this expression for this element here. Again, this element is an idempotent fixed by the evolution. And again, we have a good code for these parameters here. The length 21 and the rank, or in this case, exactly precisely the dimension of the code is 6. The best code known for this length and dimension, this code has to be weight equals to 12. Okay. Another field of 7 elements. Again, we have another important. But here, in this case, it's interesting case because the code generated by this idempotent is a good code, and also the code generated by 1 minus And this is the dual code of the code of the previous one. And we have obtained two good codes here from the same twisted group object. Okay? So, if we replace the field by commutative ring, the natural one, it's zeta 4, for example. And the second group here has order 19. We obtain here over this ring good codes, but in this case, the dual code is also a good code, but both are NDS codes, which means that these codes achieve the singleton bond. Okay? It's true for the code generated by idempotent, and it's true also true. Okay? Oh, one more example here. Zeta 8. The cyclic group here is at order 3. Idempotent again. The code generated by this idempotent and its dual are both are also MDS codes inside this. Okay? And this happens when we are considering the Euclidean product inner product. What can you say about the Galois form, or K different from 0? So we have some characterization here. We have to put this condition here just to have an evolution inside this algebra. And a code here, a lambda constacyclic, it's a K generalized Galois LCD code, if and only if, of course, the code has to be generated by an idempotent, and this equality holds, and the mapping sigma, it's an automorphism of the ring R, and we can extend this mapping to the twisted group algebra in this way. So we have here some AG bar. So this sigma K in A is just sigma K AG bar. And this equality has to be true. And we retain an example that this kind of situation works well in a string ring. So consider that F4 final field with 4 elements. We just take some element, new potent element, index 2, and we can produce a ring in this way, and 4 plus u and 4. And inside this ring, we can find this element here, and this element here has order 2. And if we consider this mapping defined in this way, this mapping is an automorphism of the ring, this ring, and this element here, it's fixed by this automorphism. Of course, it's fixed by always all powers of the automorphism. So if we consider this element, it's idempotent fixed by the involution. So since the automorph fixed the element, our powers fix the element, and always we have this equality. So the code generated by this element is K generalized LCD code for all powers of K. And this code it's doable. K-dual, in this case, it's both MDS codes with this parameters. Okay. Now, thank you very much.
Comments, questions, suggestions?
Thank you for the very nice talk. So I have a question first, and a difficult question.
All right.
That question is in the example that you have, like MDS codes, is that over FP, right? Like the characteristic of the ring, but not clear for me.
No, yeah, all the examples we have MDS are in characteristic too. Because I was going to ask you exactly that. Yeah, because G4, F4.
But the worst part,
Characteristic two.
Yeah, it's two, characteristic two, MDS.
Yeah, like the other phrases
So-
MDS.
MDS is probably is characteristic too.
Yeah, just in this two.
And over F2, that's the point. With Q.
No. Over the real.
Huh?
I mean, also F2 linear subspace, right?
Not necessarily. Not necessarily. It's here, here, codes are just R submodule or R to the n submodules. Not exactly a vector field.
But in this case, you have an analog of MDS conjecture.
What?
Because when you have MDS codes over F2, you have the analog.
We have the definition of MDR code. Just an extension to of the definition of MDS code. MDS code is defined by codes over field.
Yeah.
Okay. When you replace the code by commutative rings, commutative is the, I believe it is, or I hope it's the most important case. We have the codes called MDR codes. This the single bound is exactly the same bound for the over finite fields. Okay, but in this case, when LCD codes are free, or just the codes not to be LCD, but when the codes are free, the definitions are the same. Okay, the code has to be free, and if the code is MDR, achieves the generalized single bound, and the code has to be MDS in this the sense of fields. Okay.
In this case, so what is the analog of the MDS conjecture?
MDS is the code that
Conjecture.
There is a conjecture about the size of the length of
really
the
don't.
code over finite field, but
it's not a real Simeon ball didn't put
Or Q equal B.
for people be okay.
The only breakthrough we have, like standard,
Only for one. Okay.
So that's why.
Maybe he can show you later this.
Yeah.
It has been around in
Ah.
finite field, finite geometry, finite.
I really don't.
Yeah, that's why I wanted to understand where.
Yeah.
Because really.
I have a simple question. No, my question
That was a double question, or?
That was it.
Do you have always predicted when you have MDS codes, or
I really don't.
Yeah,
in your construct?
my question will be the same question. Can you prove that in characteristic two you always get MDS? All the examples you get. So that's always going to happen.
We need to be careful here, because if we consider characteristic 2 over F2, we just have the group modules. Okay.
But here you have a ring like
Yeah.
before, so
Yeah, the difference here, when we consider this Z4, or just other kind of link. Because if we know very well, the units, the group of units of this ring, it's cyclic 1. Okay, so we have just one subgroup of order 2. So in this case, in odd, in all the characteristics, we have just cyclic and constacyclic codes. Negacyclic codes.
So this is why we look at this.
Yeah. Yeah. Another question or?
Yeah, no, I think it was having treated already, because LCD is very close to, it's different condition, not intersection with the dual, but the dual inclusion. But the quantum codes, there is this condition of with the short Calderman and Stene, I think. Anyway, that you can have quantum codes if you have some sort of not complementary, but the dual has to be contained, a self-contained of the dual side. So have you tried this here?
I didn't mention, but we can prove in this case if this product is equal 0, or some case with the automorphism. This implies the dual code is contained in the code.
Yeah.
And the next thing is go to the tables of Marcus and see if you can beat.
And with this condition, we can produce in some way quantum.
You definitely should go to the table, because these tables are being looked, and you may be having some entrance there where you can provide better codes.
This is our next step.
So you got that.
And I think that using this Galois in your product is something very hot. And people are using this, the tenant
Yeah. So
in our case, the expert in quantum codes is ANDRÉ. He should be here, but but it's our next step for sure.
I think we can just talk with him later, then we can move on. Okay, so one has questions. Let's thank again